Prime numbers have been pretty fascinating, and mathematicians for centuries have tried to understand some hidden patterns if there exist any. Unfortunately, there haven't been many significant progresses in understanding the patterns hidden in primes, but we do have some really fascinating concepts. Let's try an exercise. Is 45,673 a prime number? Doesn't sound too easy. We can use the brute force method though, but there's another way. What if we have a look on the sum of its factors? If it's prime, then obviously that would mean we would get that number plus 1. Now we need to figure out a way to find the sum of the factors of numbers. Now what's the sum of the factors of 8? Simple. 1 plus 2 plus 4 plus 8, which is 15. Now let's observe something really interesting. The sum of factors of 7 plus the sum of factors of 6 minus the sum of factors of 3 minus the sum of factors of 1, which is 8 plus 12 minus 4 minus 1, which equals 15. Might be a coincidence, right? Let's take another example. What about 9? The sum of factors is 13. But the same sum with 8, 7, 4 and 2 will give 15 plus 8 minus 7 minus 3, which is 13. Quite interesting. Might not be a mere coincidence. Leonhard Euler had written an amazing paper on this exact idea, an amazing discovery on the sum of factors of numbers. Let's jump right into it. Now, using this method, we can easily find out if a number is prime or not. For a prime number, the sum of its divisors is that number plus 1, whereas for the case of composite numbers, the sum is bigger. Now instead of writing sum of divisors every time, let's use this integral notation as was used by Euler to represent the sum of divisors of a number. For example, if I write int 15, that would mean 1 plus 3 plus 5 plus 15, which is 24. Now let's have a look on some of this notation's important properties. For any two primes a and b, int a times b would mean 1 plus a plus b plus ab, which can be written as 1 plus a times 1 plus b, which is nothing but int a times int b. In general terms, we can write the following. Now for a power of prime, say 2, it would be 1 plus a squared. Well, that's a geometric progression and can be written as a cubed minus 1 over a minus 1. Hence, for a general n, we can write the following. Therefore, for any general integer, we can write this. Now let's come to the main relation. Whoa, this looks so strange. How do we get the sum of the factors of a number from this relation with seemingly random integers with plus minus signs occurring in period of 2? Well, it's not actually random. And there's some really fascinating stuffs which gives us this relation. Let's have a look on some examples just to convince yourself that this expression makes sense. You might have a question regarding int 0. Well, it just gives back the actual number to whose sum it belongs. We will come back to it later, trust me. After having a look at these examples, it seems that it might not be a mere coincidence. Let's now have a look on how we can achieve this relation. Remember Euler's work on partitions? There he had mentioned this particular expression which expands to give the following. Euler had mentioned that he was not able to prove the exact equality of these two expressions apart from manually expanding it. Now, expanding it's tough, but it's verifiable up to a few terms. You probably have started to note a similar pattern in the signs and the exponents. Now things are going to get interesting. Let's take the first expression for now and call it s. Let's apply logarithm on both sides and differentiate it. In the next step, we will divide the expressions by minus dx and multiply x on both the sides. Great. This expression is important, so let's take a note of this and keep this aside. Now let's deal with this expression. Let's differentiate both sides with respect to x. Let's divide both sides by s and multiply with minus x. Now, we have these two expressions which have the same left-hand side. Let's call it t. Thus, these two expressions are exactly the same. These are important as we will be using them in future. So, let's keep them in mind. Now, recall the formula for geometric progression. Yep, that's it. Now, have a look on the first expression. The first term of this expression can be written as a geometric progression. Similarly, for the next term, we can write the following, and so on. Now have a look on the different coefficients of a power of x, say x to the power 6. We note that these all are the factors of 6. Notice that similar is the case with other powers. Therefore, the final sum that we get looks like this. Now let's keep this aside for now and focus on the second expression we had got. Cross multiplying and bringing the terms on one side. Now we have the expression for t already. Let's substitute it. We get something like the following. Now, if we have a look on the coefficients of any random power of x, say x to the power 6, we note that this implies the following. And for any general n, comparing the coefficients of x to the power n, that would give us the following final expression. Now you still might be a bit uncomfortable with int 0, which even Euler considers to be the strangest part of his paper. But he defines it to be that anyway. He says that his reasoning might be a bit far from a perfect proof, but it does give an idea regarding this strange and beautiful expression which he came up with.